Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. Salam. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the pressure exerted by 1.0 mole of ethane behaving as a van der Waals gas when it is confined under the following condition. The condition is at 273.15 Kelvin in 22.414 dm cube. So the first thing you have to note is that we've been given a bunch of parameters and we've been told that we're dealing with a van der Waals gas. So for a van der Waals gas, we are asked to find the pressure. Now, the first thing you do is for you to write out all the parameters you were given. You were given the number of moles, which is 1.0 mole, okay? We were given the temperature to be 273.15 Kelvin. You were given the volume to simply be 22.414 dm cubed. Of course, the identity of the gas is 2C2H6, so it's ethane. Now, the next thing you're going to do is for you to write out the van der Waals equation. The van der Waals equation to determine pressure is P equals RT, R being the gas constant, T being temperature, divided by the molar volume Vm minus B, okay, minus A divided by Vm squared. Now, I want to quickly mention this. I know I just said B. B is a van der Waals parameter and A is also a van der Waals parameter. The V van der Waals parameter involves excluded volume while A involves attractive forces. So as you can see from the information we have, we know the gas constant because it's constant. We know the value for temperature because we're given the question. We know the value of volume, but not the value of molar volume. But because we're given the number of moles, we can always determine the molar volume, which is just simply molar volume, okay? It's just simply volume divided by number of moles. And we're given the volume to be 22.414, okay? dm cubed divided by the number of moles, which is just simply 1.0 mole. So what you end up with is just 22.414 dm cube per mole. So that is basically the answer. So that is it. So now we have the value for Vm now, and of course Vm squared. Now what is left for us is for us to say what is A, because we need A and we also need the value for B to determine the value for P, because when we have the value of A and B, that's when we can substitute with other values to determine pressure. So it's important for you to know that for van der Waals gas, the values of A and B is unique for each gas. So that means that for me to know what the van der Waals parameters A and B is, I have to look for what what it is for ethane. So like for example, we're given H2 gas or O2 gas, is going to be different from gas to gas. So looking at the Atkins Physical Chemistry 11th edition textbook, I would look at the resource section, which is at the back of the textbook, and I determined that the value for A is simply 5.507 atmosphere, okay, dm6 per mole squared, okay, and then value for B is simply 6.51 times 10 to the power of negative 2 dm cubed per mole. So that is it. Note that this textbook, in case you have a physical chemistry Atkins 11th edition textbook, has the resource section at the back of the textbook, and all the information you need to solve all the questions in the chapters of physical chemistry is there, just like this parameters A and B is also there. So now we have all this information, we can just simply substitute. But before I go on to substitute, let me rewrite the equation and then we can continue from there. So P is equal to RT, molar volume minus B minus A divided by molar volume squared. So P equals R is 0.08206 dm cube atmosphere divided by mole Kelvin times the temperature. So what is the temperature? We have the temperature to be 273.15 Kelvin. So that will be 273.15 Kelvin, okay, divided by the molar volume, which is 22.414 dm cube per mole. So 22.414 dm cubed per mole, okay, minus B, which is just 6.51 times 10 to the power of negative 2 dm cubed per mole. Our work, of course, is not done because we have this information here that we haven't substituted. So I'm going to say a minus here, a big minus. And then, of course, the value for A, we know that to be 5.507. So 5.507 atmosphere dm raised to the power of 6, okay, per mole square, or I'll just say mole raised to the power of negative 2, divided by Vm square, which is the molar volume square. Molar volume is 22.414 dm cube per mole. So that will be 22.414 dm cubed per mole all squared. So this is basically what we have. Yeah, that's how we do it. So let me start canceling whatever I can cancel. I can cancel out the Kelvin here. So we can, go on to math since we have successfully substituted everything. So I'm going to say pressure equals the numerator 0.08206 times 273.15 would give us 22.41469, okay, dm cubed atmosphere per mole, okay, divided by 22.414. So this one at the bottom is what I'm trying to do. dm cube minus 6.51 times 10 to the power of negative 2, which is just simply 22.3489 dm cube per mole. So we've subtracted the information at the bottom. So this minus the other part of the information, 5.507 atmosphere dm6 per mole squared, okay, divided by 22.414 dm cubed per mole all squared. That's going to give you 502.3874, okay, dm6 per mole squared. So that is it. Yeah, so you have the information so far. Of course, now we can cancel out more units. So cancel out dm cube, mole, mole, and of course dm6 mole squared, mole squared. So you end up with 22.41469 divided by 22.3489 atmospheres. When you do that division, you end up getting 1.002944 atmospheres, okay, minus 5.507 divided by 502.3874 atmospheres. Of course, when you do that division and you put on your calculator, you end up getting 0.010962 atmospheres. So the pressure would end up being 0.991982 atmospheres. So, of course, because of this is a chemistry question and we're chemists solving a question, you know that you're not going to leave this in this amount of raw values. You have to pick the lowest number of significant figures for the values that we're giving the question, and that determines the number of significant figures for your final answer. So what this is that we're going to go back to the parameters we used to solve the question and see the lowest number of sig figs that we used. So we see that we're given number of moles, 2 sig figs. Here we have 5 sig figs for volume, 5 sig figs for temperature, 4 sig figs for A, 3 sig figs for B. Well, the one with the lowest number of significant figures is the number of moles, so that's 2 sig figs. So we have to put our answer in 2 sig figs. So the value for pressure would be 0.99 atmospheres. And this is how you answer this question. So I have done another question very similar to this, where the values are different, but the concept is the same. So make sure you watch that video. The question is going to be on the screen right now. Yeah, if you have any questions, please put in the comment section. If you have any concerns or suggestions, also put in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, calculate the pressure exerted by 1.0 mole H2S behaving as a van der Waals gas when it is confined under the following condition: 500 Kelvin in 150 centimeter cube. So calculate the pressure exerted by 1.0 mole of H2S gas. The first thing you have to note is that this H2S gas, we're told that it acts as a van der Waals gas, and they told us the number of moles for this gas is 1.0 mole. We're also told that it was confined under the following condition, which is just the temperature, which is 500 Kelvin. And then we were told that the 500 Kelvin was in 150 centimeter cube. So 150 centimeter cube. And we're told to determine pressure. Now, the first thing you have to notice, because this is a van der Waals gas, you already know that to find pressure, there's just one equation that we use, which is pressure equals RT, where R is the gas constant, T is the temperature, is equal to the molar volume minus B meaning the one of the van der Waals parameters, and then minus A, which is the second van der Waals parameter, divided by molar volume all squared. We're lucky enough that we have the R, we have T, R is the gas constant, so constant value is a constant. T, we have that as 500 Kelvin. We have the volume. We have, yeah, we have that, but we don't have the A and B given to us. Now, whenever you see a question like, it's important for you to know that at the back of the physical chemistry Atkins textbook, which is a textbook I got this question, there is a resource section, and in that resource section, you get all of the information you need for each question. So when you go to the back of the textbook and you look for the A and B for H2S, you're going to get those specific values for A and B. So looking at the back of my textbook, I basically determined that the value for A, the van der Waals gas, is 4.484 atmosphere dm6 raised to the power of mole squared. And then the value for B was just simply 4.34 times 10 to the power of negative 2 dm cube per mole. So that's basically it. So now we have the value for A and B. And the thing that makes sense is that, okay, I told you guys already about volume, right? You know, we have the value for R, T, A, and B. And then we also have the value for volume. But this question is asking us for molar volume. And to determine molar volume, you have V equals, sorry, the molar volume, you have Vm. So molar volume is equal to the volume divided by number of moles. But then there is an issue. The issue is simply this. We see that the parameters that we're given is dm, the unit for volume is decimeter, and then the unit for volume for B as well is also decimeter or decimeter cube. But then our question is telling us 150 centimeter cube. So we cannot go ahead and just find the molar volume. We have to first of all convert from centimeter cube to decimeter cube. So we have to go now from centimeter cube, so 150 centimeter cube is going to give you what in decimeter cube. So that is what is the requirement. So let's remember 10 centimeter is going to equal 1 decimeter. So let's do a quick conversion refresher. And then you have 10 centimeter is equal to 10 centimeter is equal to 1 decimeter. So 10 centimeter cube is equal to how many decimeter cube? So you have 10 times 10 times 10 will give you 1000. Centimeter times centimeter times centimeter will give you centimeter cube. And then 1 times 1 times 1 give you 1 decimeter times decimeter times decimeter is decimeter cube. So 1000, okay, centimeter cube would give you 1 decimeter cube. Hence, you're giving 150 centimeter cube. So 150 centimeter cube would give you what? X, right? So let's cross multiply. You have 1000 centimeter cube X is equal to 1 decimeter cube times 150 centimeter cube. So you divide both sides by 1000 centimeter cube. So you end up with canceling out the left side, and then you cancel out centimeter cube here, centimeter cube here, 5 here, 5 here. So you end up with X equals to 115 divided by 100 decimeter cube, which is the same thing as X equals 0.15 decimeter cube. Now, let's not forget X is just simply volume. So V is equal to 0.15 decimeter cube. Now we've successfully found what volume is in decimeter cube. Now we can now determine the molar volume. So molar volume is just volume divided by number of moles. So that would be 0.15 decimeter cube divided by number of moles, which is 1.0 mole. So divided by 1.0 mole. So the molar volume is just going to be 0.15 decimeter cube per mole. So successfully, we've determined what the molar volume is, and we have all the parameters that we need. So I'm just going to quickly rewrite all the parameters so we don't have to keep going back and forth. So let me just give me like 2 seconds. Let me just rewrite it. So you have the temperature is 500 Kelvin. A is 4.484 atm dm6 per mole squared, and then B is 4.34 times 10 to the power of negative 2 dm cube per mole. And then, of course, R is the gas constant. So now, substituting, we have P is equal to RT divided by Vm minus B minus A divided by Vm squared. So we're going to substitute all of this information in this equation. So you have the gas constant P is just simply 0.08206 dm cube atmosphere divided by mole Kelvin times temperature, which is just 500 Kelvin, divided by Vm. So molar volume is 0.15 dm cube per mole minus B, which is just 4.34 times 10 to the power of negative 2 dm cube per mole. So minus A, which is just 4.484 atm dm6 per mole squared divided by Vm squared. So that would be 0.15 dm cube per mole all squared. So yeah, that's it. So of course, let's simplify. I can cancel out the Kelvin. That's how far I can simplify. I have to do the multiplication first to make this simplification easier. So next I work with the numerator right here. 0.08206 times 500 will give me 41.03 atmosphere dm cube. Of course, I'm just rewriting the rest of the units per mole. So that's the first one. And then you've got the denominator, which is just 0.15 minus 4.34 times 10 to the power of negative 2 is just 0.1066 dm cube per mole minus 4.484 divided by 0.15 dm cube per mole all squared would simply be, so let me just write 4.484 dm6 atmosphere per mole squared divided by 0.15 dm cube per mole all squared would just be 0.0225 dm6 per mole squared. So cancel out dm cube, dm cube, dm cube, dm cube, mole, cancel out dm6 mole squared. So you can see on both sides that you have atmosphere remaining here and atmosphere remaining, which makes sense. And that hints to us that work is being done correctly, mainly because the units for pressure is atmospheres. So P is just simply going to be 384.8968 atmosphere minus 199.28889 atmosphere. So pressure is just simply 185.6079 atmosphere. I also wanted to mention that, like, while this is very correct, let's not forget that we're dealing with a chemistry question here. We cannot just leave information, our final answer, in just a bunch of raw values. We have to approximate. And to approximate, we have to pick the lowest number of significant figures, and we approximate to that lowest number of significant figures. So if we go back to our question and see the values we're given, number of moles was in 2 sig figs, and then we have temperature in 3 sig figs, and then of course volume in 3 sig figs. So what this is telling you is that 2 sig figs is the lowest number. We have to approximate to 2 sig figs. So approximating to 2 sig figs right here, I can just simply have, I'm going to do it in scientific notation. So what I end up with is pressure is equal to 1.9 times 10 raised to the power of 2 atmosphere. So this is basically the answer to this question. 1.9 times 10 raised to the power of 2 atmosphere. So yeah, that's it. That's basically the answer. If you have any questions, please put in the comment section. I have done a very similar question on this channel, and it's currently on the screen. So make sure you check the description box and click on the link so that you can watch that video and get more practice done. If you're a student who's struggling in any of your STEM related courses or trying to improve and succeed, make sure you email me at shahabitutoring@gmail.com. I help students in middle school, high school, and college to succeed and be the best version of themselves in academia. I also help mentor students who are trying to navigate their academic life and career path. So if you would like my services, and I've been told I'm a great tutor and mentor, make sure you email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, calculate the pressure exerted by 1.0 mole of H2S behaving as a van der Waals gas when it is confined under the following conditions: at 273.15 Kelvin in 22.414 dm cube. So the first thing we have to notice is that we're told that we're dealing with a van der Waals gas, and we're also given the number of moles of gas to be 1.0 mole. And we're told that it was confined under the following condition, where we're given the temperature to be 273.15 Kelvin, and then the volume to be 22.414 dm cube. So since you know that we're dealing with a van der Waals gas and we've been given the number of moles, the temperature, the volume, the next thing you have to do is to write out the formula for determining pressure of a van der Waals gas, which is just simply pressure is equals to RT divided by the molar volume minus the parameter B minus A, which is the second parameter of the van der Waals gas, divided by Vm squared. Of course, R is gas constant, T is temperature, Vm is molar volume, and this is the formula we're going to need to be able to solve this question. So the first thing you have to note is that we know the gas constant R because it's a gas constant. It's a constant, so it has like the value, known value. We know the temperature because we're given the question. We know the volume, but we're told to determine the molar volume here. So when you're asked to determine molar volume, when you're given volume, the molar volume is just simply the volume divided by the number of moles. We're given the volume to be 22.414 dm cube and the number of moles to be 1.0 mole. So hence the molar volume is just simply 22.414 dm cube per mole. So that is basically the molar volume. So now we have the molar volume, the gas constant, and the temperature. Now we have to um, get the values for A and B to determine the pressure, because of course when we've determined the value for A and B and we substitute those values as well as the values for R, T, and Vm, we can determine the value for pressure. So according to the Physical Chemistry Atkins textbook, the 11th edition, which this question is from, the resource section of that textbook shows you the A and the B values for all gases. In this case, we're dealing with H2S. So looking at the A and B value, the van der Waals parameters for H2A gas, we determine A to be 4.484 atmosphere dm6 per mole squared, while B is simply 4.34 times 10 to the power of negative 2 dm cube per mole. So these are the values that we need for this question. So now we've been able to successfully determine all the parameters that we need to solve this question. We just can simply substitute. So we have pressure is now going to equal RT, which is just 0.08206 dm cube atmosphere per mole Kelvin, divided by, sorry, not divided by, times actually, if I almost forgot temperature, times the value for temperature, which is 273.15 Kelvin. So times 273.15 Kelvin. Okay, all of that information divided by Vm minus B. So the molar volume 22.414 dm cube per mole. Okay, minus the value for B, which we know to be 4.34 times 10 to the power of negative 2 dm cube per mole. So that is the other one. So all of that information minus A, which is 4.484 atm dm6 per mole squared, okay, divided by Vm squared. So what is Vm? Molar volume is 22.414 dm cube per mole. So 22.414 dm cube per mole all squared. So now this is basically what we really needed, right? We've successfully substituted everything. So now all we just have to do is to simply cancel out whatever we can cancel out. We have per mole Kelvin here and we have Kelvin, so the Kelvin can cancel out. So we've successfully canceled that out. So we're just simplifying as best we can. So next we have pressure is equal to 0.08206 times 273.15. When you do the calculation, you end up getting 22.41469. And then of course we have the atmosphere dm cube. So I'm just going to say atmosphere dm cube per mole, okay? And then you have the denominator. We're going to do the calculation. 22.414 minus 4.34 times 10 to the power of negative 2, which is just 22.3706 dm cube per mole, okay, minus 4.484 atmosphere dm raised to the power of 6 per mole squared. So that would be 4.484 atmosphere dm6 per mole squared, okay, divided by 22.414 dm cube per mole all squared is simply 502.3874 dm6 per mole squared. So of course you cancel out dm cube, mole, you cancel out dm6 mole squared. So we've canceled. So now we've canceled out all of the units, right? And now we can just focus on determine the answer for pressure. Like, for example, we have atmosphere is the only unit that remains. Atmosphere on this side is the only unit that remains, which confirms the fact that we're doing our calculations correctly. So let's say pressure now is just going to be 22.41469 divided by 22.3706 will give you 1.00197 atmosphere, okay, minus 4.84 divided by 502.3874 would give you 0.0089254 atmosphere. So of course, when you input this information in your calculator, you end up with 0.99305 atmosphere, which you can successfully approximate to two sig figs, because in chemistry you can't just leave your question with the raw value. You have to put the lowest number of significant figures you got from the calculation, and we can see the lowest number of significant figures is two sig figs because the number of moles was two sig figs. The volume is 5 sig figs, the temperature is 5 sig figs, so the number of moles takes the cake, and it's gonna be our answer has to be in two sig figs, the final answer. So the pressure is just 0.99 atmosphere. So this is the answer to this question. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the pressure exerted by 1.0 mole of ethane behaving as a van der Waals gas when it is confined under the following conditions, or the following condition, which is just 1,000 Kelvin in 100 centimeter cube. So the first thing we have to note is that we've been told that we're dealing with a van der Waals gas, and whenever you're dealing with a van der Waals gas, we're not going to use the perfect gas equation. So the first thing we have to do is to write out the parameters. We're told the number of moles is 1.0 mole. We were told that the temperature is 1,000 Kelvin. We're told the volume is 100 centimeter cube. So we're told to determine the value for pressure, or the value for pressure. So the first thing you do is for you to remember that whenever you're dealing with whenever you're dealing with a van der Waals gas, when you're asked to determine pressure, there's just one formula that we use, which is pressure is equal to RT, so the gas constant, times temperature divided by the molar volume minus the parameter of the van der Waals, which is B, minus another parameter A divided by the molar volume squared. So A and B are parameters for the van der Waals gas that is unique to that particular or specific gas. So basically it's like a fingerprint, right? So that's just basically what I'm trying to say here. The first thing you notice is that we have the gas constant because the constant R. We have the value for temperature, 1000 Kelvin. We have the value for volume, not molar volume, but we can determine the value for molar volume, right? By just having volume divided by number of moles. So we have volume, we have number of moles. So basically we have molar volume, but we don't have the value for A and B. Well, this is great news because we're using the Atkins Physical Chemistry 11th edition textbook. At the back of the textbook, there's something called resource section. So hence we have the value for A and the value for B at the back of the textbook. So the value for A, the van der Waals parameter A is equal to 5.507 atmosphere dm raised to the power of 6 per mole squared, and then the value for B is just simply 6.51 times 10 to the power of negative 2 dm cube per mole. So yeah, that's it. Now we have A, thank God, and we also have B, or we have B and then we have A. Now I want to say something. The normal thing would be for us to substitute, but then we have an issue. We see that our units do not match for volume. We see for A, we have a dm raised to the power of 6, and then we have a dm cube. Hence, we have the unit decimeter for the values of A. But then in our volume, we have centimeter cube. We cannot proceed by substituting. We have to convert from either cm cube to dm cube or dm cube to cm cube. But what is better is for us to convert from cm cube, right, to dn cube. So that's basically how we're going to do it. So let's not forget that 10 centimeter gives 1 decimeter. So 10 centimeter cube would just be 10 times 10 times 10. So that would be 1000 centimeter times centimeter times centimeter cube equals this 1 decimeter cube as well would just be 1 times 1 times 1. That's 1 decimeter times decimeter times decimeter, which is decimeter cubed. So we have that. Now we have the standard for conversion. Now let's go back to our question. We see that we have 100 centimeter cube. We have to go from 100 centimeter cube to decimeter cube. So we have 100 centimeter cube here, and let's just say we have x here. We would cross multiply to end up with 1000 centimeter cube x equals 1 decimeter cube times 100 centimeter cube. Divide both sides by 1000 centimeter cube. Divide both sides by 1000 centimeter cube. So you cancel out 1000 and centimeter cube and 1000 centimeter cube. So you end up with x is equal to, we cancel out the centimeter cube. We, of course, 100 here, 1, 1000 here, 10. So you end up with x equals 1 over 10 decimeter cube, which we can just say x is equal to 0.100 decimeter cube. So we have successfully determined the volume to be 0.100 decimeter cube. So now we have volume. Next thing we have to do is to determine molar volume. Like we've said, molar volume is just simply volume divided by number of moles. So volume will be 0.100 decimeter cube divided by the number of moles, which is 1.0 mole. So what we end up with is 0.100 decimeter cube per mole. So that's it. That is 100% it. Now, we've successfully done a lot. The next thing we have to do now is to substitute, because now we have the molar volume in the proper units. So to do that, just to make our work easier, let me just write out all of the parameters. We have the temperature is 1000 Kelvin. We have the A value to be 5.507 atmosphere. I'm only rewriting this honestly so I don't have to go back and forth up top, because it's going to be confusing to everyone watching if I have to like keep going up and down, up and down, up and down. It's going to be very annoying and confusing. So that's why I'm just rewriting this. So you have B is just 6.51 times 10 to the power of negative 2 dm cube per mole. So yeah, now we're going to substitute. P is equal to, we're going to substitute into this. P is equal to RT Vm minus B minus A Vm squared. So we start substituting. So pressure is equal to 0.08206, which is the gas constant, the unit ATM dm cube per mole Kelvin, okay, times the temperature. We have our temperature to be 1000 Kelvin. All of that information divided by Vm minus B. So the molar volume, we know that to be 0.100 dm cube per mole, okay, minus B, which is just 6.51 times 10 to the power of negative 2 dm cube per mole. So yeah, that's the second one. Of course, to just break down our work, let's cancel out the Kelvin. So yeah, that's it. Let's not forget that we just put the first part. The second part is minus the value for A. We know that to be 5.507 atmosphere dm 6 per mole squared, okay, divided by Vm squared, which is just 0.100 dm cube per mole, all squared. Yep, that's it. So we're just going to simplify. So 0.08206 times 1000 Kelvin is just simply 82.06 dm cube atmosphere per mole, okay, minus, sorry, divided by, first of all, the denominator, which is just the addition of 0.100 minus 6.51 times 10 to the power of negative 2. So we're going to be focusing on the denominator. When you put this information, this subtraction in your calculator, you end up getting 0.0349 dm cube per mole. So minus 5.507 atmosphere dm raised to the power of 6 per mole squared, divided by 0.100 dm cube per mole all squared, which is just simply 0.0100 dm dm raised to the power of 3 squared is just dm6. Mole squared is just, or mole times mole is just mole squared. So of course we cancel out dm cube here, mole here, dm6 here, dm6 here, mole squared, mole squared. So pressure is equal to 82.06, its atmosphere divided by 0.0349, which is just 2351.2894 atmosphere, minus this division here, which is 5.507 divided by 0.01, which is just 550.7. And then, of course, we still have atmosphere here, just like we did over here. We have atmosphere here. So I'm just going to put that down. So atmosphere. So we just do a simple subtraction in an input that in our calculator. So we have 1800.5894 atmosphere. And of course, in chemistry, we can't just put this information and be like, yeah, this is our answer. We have to put in the lowest number of significant figures based on the raw values we're given in the question. So going back up top, we're given the number of moles, 2 sig figs. So then we have temperature, which is 4 sig figs, and volume 3 sig figs. So the lowest number is 2 sig figs. That means our final answer has to be in 2 sig figs. So that will be, it's going to stop here. So pressure is approximately 1.8 times 10 raised to the power of 2 atmosphere. Sorry, 1.8 times 10 raised to the power of 3 atmosphere. So that is the value for pressure of the van der Waals gas for ethane. If you have any questions, please do not hesitate to put in the comment section. That also goes for concerns as well as suggestions. If you like this video, please subscribe and like it. I also wanted to mention that for any of you who is struggling or is trying to improve or succeed in any of your STEM related courses, whether you're in middle school, high school, or college, make sure you email me at shahabitutoring@gmail.com. I help students be the best version of themselves in their academic career. I also help with mentoring services as well for students who are trying to navigate their career and academic life. So I've been told I'm a great tutor and mentor, so do not hesitate to email me at shahabitutoring@gmail.com. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, suppose that 10.0 mole of C2H6 gas is confined to 4.860 decimeter cube at 27 degrees Celsius. Predict the pressure exerted by ethane from 1, the perfect gas, 2, van der Waals equations of state. When you're done solving the van der Waals equation of state, you're asked to calculate the compression factor based on these calculations. So the first thing you have to do is for you to write out the parameters that we're given. So we're given the number of moles to be 10.0 mole. The identity of the gas is ethane, so C2H6 gas. We're also told that it was confined to 4.860 decimeter cube. So that's the volume. The volume is 4.860 decimeter cube. And of course, the temperature is 27 degree Celsius. Of course, we will go from degree Celsius to Kelvin. So it's going to be T is just 27 plus 273.15, and therefore temperature ends up becoming 300.15 Kelvin. Now we have all of the parameters that were given written out. We have the number of moles of volume, the temperature. We can determine the pressure as we've been told to determine using the perfect gas equation. The perfect gas equation is just simply PV equals nRT, and therefore pressure is equal to nRT divided by V. So therefore pressure is equal to the number of moles, which is just simply 10.0 mole, times the gas constant, which is just 0.08206 dm cube atmosphere per mole Kelvin, times temperature, which is 300.15 Kelvin. So all of that information divided by volume. So V is equal to 4.860 dm cube, 4.860 dm cube. So of course we cancel out the number of moles, we cancel out the unit for the moles, cancel out the unit for volume, dm cube, cancel out Kelvin, and when we simply do this, we just end up with pressure is just equal to 10.0 times 0.08206 times 300.15 divided by 4.860. All of this information is just atmosphere. So when you have this, you just have pressure is equal to all of this information. And when you input this information in calculator, you end up getting pressure is equal to 50.67465 atmosphere. So of course the next thing you have to do is to look at the number of significant figures that we're given, and we pick the lowest number of significant figures. Whatever that number of significant figures is what we're going to apply to our final answer. So what I mean is, for example, we have this information here is 3 sig figs. So the number of moles is 3 sig figs. The volume is 4 sig figs. The temperature is 5 sig figs. So we have to put our answer in 3 sig figs. So when we do that, we end up with the pressure being approximately 50.7 atmosphere. So this is the answer to this first part of the question. Second part of the question requires us to use the van der Waals equations of state. And thankfully, we have the information that we need. The next thing you have to do is just simply write out the van der Waals equation of state. So the van der Waals equation of state, so this is the second one we're doing, is pressure is equal to RT, so gas constant, times temperature divided by the molar volume minus B minus the parameter A divided by the molar volume squared. So we have the pressure is what we're looking for. We have the R, the gas constant, to be 0.08206 dm cube atmosphere per mole Kelvin. Okay. We have the temperature to simply be 300.15 Kelvin. We have the volume to simply be 4.860 dm cube. So the molar volume, which is just the volume divided by number of moles. So volume divided by number of moles would just be 4.860 dm cube divided by the number of moles, which is just 10.0 mole. So we end up with 0.4860 dm cube per mole. So that is basically the answer to that molar volume. So you have the molar volume, the gas constant, you have the temperature. So half of our work is done. So for example, we have the gas constant, the temperature, the molar volume, but then we don't have the value for B and value for A. From the question, we're not given the value for B, neither will we given the value for A. So what we have to do now is for us to go to the resource section of our physical chemistry Atkins 11th edition textbook and write out the value of A and B. So in the resource section, we determine A to be 5.507 dm6 atm per mole squared. And then we've got B to be 0.0651 dm cube per mole. So that's basically the information. So yeah, you have pressure. So that would be pressure is equal to RT divided by Vm minus B minus A divided by Vm squared. So pressure is just equal to 0.08206 0.08206 dm cube atmosphere per mole Kelvin times, of course, temperature, which we know that to be 300.15 Kelvin. So that's the numerator of the first part. So this part. Now we divide by Vm minus B. So the molar volume, we know the molar volume to simply be 0.4. So we know the molar volume to simply be 0.4860 dm cube per mole. So 0.4860 dm cube per mole. We know the value for B to be 0.0651 dm cube per mole. So we have successfully written this part of the equation. So then of course we have minus here. And then you have A, the value for A will be 5.507. So 5.507 dm6 atmosphere per mole squared, okay, divided by Vm squared. So molar volume squared divided by molar volume squared. So that would just be the molar volume is 0.4860 all squared. So 0.4860. Let's not forget the unit. So dm cube per mole all squared. So yeah, that's it. That's basically it. We have successfully inputted all what we need to input in the equation. And yeah, we're just gonna work with what we have. So before we go on, we can just simply cancel out the Kelvin for the temperature because those units can cancel out. So you have pressure is equal to 0.08206 dm cube atmosphere per mole times 300.15 would give you 24.63031 dm cube atmosphere per mole divided by 0.4860 dm cube per mole minus 0.0651 dm cube per mole. So you end up with 0.4209 dm cube per mole minus 5.507 dm6 atmosphere per mole squared divided by 0.4860 dm cube per mole. So that would be 5.507 dm6 atmosphere per mole squared divided by 0.4860 dm cube per mole. All squared is just 0.236196 dm cube, dm6 actually, not dm cube, dm6 per mole squared. So yeah, that's our work. We have successfully simplified it, so we can just simply cancel out the units. So you can cancel out dm cube here, mole here. So what you end up with is atmosphere, which is makes sense because we're solving for pressure. And then here as well, you cancel dm6 here, dm6 here, mole squared, and we end up with atmosphere, which makes sense because that's also what we're solving for. So now you have pressure is equal to 24.63031 divided by 0.4209 would give you 58.5182 atmosphere minus 5.507 divided by 0.236196, which is just simply 23.3154 atmosphere. So yeah, that's basically the answer. So pressure is equal to 58.5182 minus 23.3154, which is just simply 35.2028 atmosphere. So, of course, we can do this in three sig figs. So, the reason why I'm doing three sig figs is what I said earlier. The lowest number of significant figures is where you would approximate up to whenever you're given a question like this. So, if you look at our work, we have all the information that we used in solving this question. We have the gas constant to be in 4 sig figs. We have temperature to be in 5 sig figs, molar volume in 4 sig figs, the value for A to be in 4 sig figs, and the value for B in 3 sig figs. That means our final answer has to be in 3 sig figs. So the value or the answer for pressure is just approximately 35.2 atmosphere. And this is the answer to this question when you find the pressure of the van der Waals gas using the van der Waals equations of state. Now, our work is still not done because we're also told, based on the van der Waals parameters, to calculate the compression factor based on these calculations. So to calculate the compression factor, we have multiple compression factor formulas, but the one that works well with this question is, so compression factor is Z. So what works well in this question is just the compression factor formula PVM. So pressure times the molar volume equals R, the gas constant, temperature, and then Z, which is the compression factor. So compression factor Z is just simply PV sub M divided by RT. Z, which is the compression factor, is the pressure times the what they call it times the molar volume. So the pressure, we know that to be 35.2. Right now, using 35.2, I'm going to use more of the raw value just because I don't want to use the approximate value when I'm still doing calculations. I only approximate at the end when I've gotten the final answer. So I have to use the raw values. So 35.2028. So 35.2028 atmosphere times the molar volume, which is 0.4860 dm cube per mole. So 0.4860 dm cube per mole. We know the gas constant to just be 0.08206 dm cube atmosphere per mole squared. Sorry, per mole Kelvin, not per mole squared. I apologize. Times the temperature, which we know that to be 300.15 Kelvin. So write that here. So 300.15 Kelvin. So of course you cancel out the atmosphere, cancel out the dm cube to dm cube, the Kelvin, the Kelvin, the mole, the mole. And as you've seen, we've successfully cancelled out every single unit. So all we have to do is just input this information in the calculator. When we input the numerator, 35.2028 times 0.4860, we end up getting 17.108561 divided by 0.08206 times 300.1 would give you 24.63031. And is the value for Z is just simply, when you input this information again in the calculator, is just simply 0.694614. And then Z is approximately what? Well, let's first of all remember we have to use the lowest number of significant figures. We know that pressure itself is 3 sig figs, although we use the raw data. We only use the raw data in the calculation, but we also know that the is 3 sig figs for pressure. We know here is 4 sig figs, here is also 4 sig figs, and then finally the temperature is 5 sig figs. So we're going to approximate this in 4 sig figs. So we end up with 0.695. So the compression factor answer is 0.695. The only reason pressure has more than 3 sig figs here again is for the calculation to get as much of the accurate answer as possible. So yeah, this is the answer to this question. We have successfully answered the value for pressure for perfect gas, van der Waals gas, as well as compression factor. So if you have any questions, please put in the comment section. If you like this video, please make sure you subscribe as well as like it. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, in an industrial process, nitrogen is heated to 500 kelvins at constant volume of 1.000 meter cube. Full stop. The mass of the gas is 92.4 kilograms. Use the van der Waals equation to determine the approximate pressure of the gas at its working temperature of 500 Kelvin. For nitrogen, the van der Waals parameters A is equal to 1.352 decimeter raised to power of 6 atmosphere per mole squared, and the van der Waals parameters B is equal to 0.0387 decimeter cube per mole. So in this particular question, we're asked to determine the approximate pressure, okay? We're asked to determine the approximate pressure in using the van der Waals equations of state. But before we can go ahead and do that, we have to first of all write out all of the parameters that we're given. We've been given the value for A, we've been given the value for B. We've been given the value for volume, which is just 1.000 meter cubed. And of course, the value for temperature to be 500 Kelvin. We've also been given the mass of the gas to be 92.4 kilogram. Now, we have all the information that we've written down all of the information that we've been given, but then there's an issue. We have to first of all realize that we're dealing with the van der Waals equation question. So we have to write out the van der Waals equation of state, which is pressure is equal to RT divided by the molar volume minus B, so minus the parameter B, minus the van der Waals parameters A divided by the molar volume squared. Looking at this, we see that we know R because R is just simply gas constant, so it's a constant value. We know temperature, we know B, we know A, but we have volume, and so we have molar volume and then molar volume squared. But then what we're given in the question is just simply volume. We actually don't have molar volume. And for those of you who don't know, molar volume is simply the volume divided by the number of moles. So as you can see, we're not given the number of moles, but we're given the mass of the gas. So when you have the mass and you know the identity of the gas, in this case is nitrogen, we can determine the number of moles by using the molar mass and the value for the mass. So the number of moles is just simply going to be mass divided by what? Molar mass. So the number of moles here is just going to be the mass is 92.4 kilogram, but because of mass in chemistry, we prefer it to be in grams. We're just going to convert 92.4 kilograms to grams, which is just simply 92.4 times 10 raised to the power of 3 grams. And of course, the molar mass of nitrogen, we know that to simply be, well, just N2 gas. So the molar mass for N2 gas, nitrogen gas, is 28.014 gram per mole. So of course we can cancel out the grams, 92.4 times 10 raised to the power of 3 divided by 28.014 gram per mole. So the number of moles is just simply going to be this information, the numerator divided by the denominator. And when we do that, we end up getting 3,298.351 mole. So that is basically the answer to this. But let's not forget that we're not just simply to determine the number of moles. What we're actually using the number of moles for is for us to determine the molar volume. So the molar volume here is just going to be the volume divided by number of moles. So molar volume is just going to be, the volume here is 1.000 meter cube. Wow. Well, let's not forget that the value for A and the value of B that we're given in this question is in decimeter, right? And then we have the volume in meter cube. Now we have to do an extra work, which is for us to convert from meter cube to decimeter cube, because we want to have all our numerical values in the same unit, so it's easy for us to solve the question. So our work is not quite done. Like, I'm sure you guys were thinking, oh, we can just simply divide, but that's one thing with chemistry. You have to make sure, or science, honestly, you have to make sure that all of the units match. So going from meter cube to decimeter cube is what we're going to have to do here. So now going from meter cube to decimeter cube, we have to first of all not forget what 1 meter equals in terms of decimeter. So 1 meter is always equal to 10 decimeter, and that is just the value for length. Now we're dealing with volume, so we can just simply cube it, right? Because we're dealing with area, we're going to square it. So you cube it here, so you end up with 1 meter all cube is the same thing as 1 times 1 times 1, that's 1 meter times meter times meter, that's meter cube. And then 10 decimeter all cube is the same thing as 10 times 10 times 10, which is just 1,000 decimeter times decimeter times decimeter, decimeter cube. So that is basically it. Now, yeah, that's it. We've done the proper conversion. So what we end up having here is just simply 1,000 decimeter cube. So going back here, the molar volume is just simply going to be 1,000 decimeter cube divided by the number of moles, which is just simply 3,298.351 mole. Of course, you put this information in your calculator, the molar volume becomes 0.30318 decimeter cube per mole. So that is the molar volume. So we go back to our work again, and we see that the time we see from our what's it called, our van der Waals equation of state, that we have all the parameters that we need in order for us to determine pressure. We have the gas constant, we have the temperature, the value for A, value for B, and of course the molar volume. So yeah, now we can just simply substitute. So yeah, we can simply substitute. So I'm going to do it at the bottom here. So pressure is going to equal, again, RT divided by the molar volume minus B minus A divided by molar volume squared. So to do that, we have pressure is just simply RTR is 0.08206 dm cube atmosphere per mole Kelvin times the value for temperature. We have temperature here to be 500 Kelvin. So 500 Kelvin divided by the molar volume, which we know to be 0.30318 decimeter cube per mole, okay, minus B. And of course, B is simply 0.0387. So 0.0387 decimeter cube per mole. So that's it. So all of that minus, and then you have A. What is A? We substitute A. We know A to be 1.352. So minus 1.352 atmosphere dm6 per mole squared divided by the molar volume squared, which is just simply 0.30318 decimeter cube per mole all squared. So yeah, that's basically how it's done. So now, of course, let's cancel out Kelvin, cancel out the Kelvin. Yeah, we've canceled out all of that. We can now continue with our math. So 0.08206 times 500 is simply 41.03 decimeter cube atmosphere per mole. okay, divided by 0.0 divided by 0.30318 minus 0.0387 is just simply going to give you 0.26448 decimeter cube per mole, minus 1.352 atmosphere decimeter raised to the power 6 per mole squared divided by per mole squared divided by 0.30318 decimeter cube per mole all squared. That's simply just going to be 0.091918 decimeters to the power 6 per mole squared. So yeah, that's how it's done. Cancel out decimeter cube, cancel out decimeter cube, cancel out mole, cancel out mole, cancel out decimeters to the power 6, decimeter raised to the power 6 divided by mole squared and then mole squared. Yeah, so you've canceled out all of the units, only the unit that you need, which is just atmosphere, because we're actually solving for pressure. So that just makes sense. So 41.03 divided by 0.26448 is simply 155.1346 atmosphere minus 1.352 divided by 0.091918, which is just simply 14.7087 atmosphere. So of course, you solve this, pressure ends up being 155.1346 minus 14.7087. You end up getting 140.42584 atmosphere. And of course, because we are chemists, scientists, we have to put it in the lowest number of significant figures based on the values that were given at the beginning of the question. So the lowest number of significant figures, we have 500 in 3 sig figs, 1.000 meter cube in 4 sig figs, this one in 3 sig figs. So our final answer has to be in 3 sig figs. So it's going to stop here. So the value for pressure is going to be approximately 140 atmosphere. So this is the answer to this question. So yeah, that's basically the answer. If you have any questions, please put in the comment section. If you have any suggestions or concerns, also put in the comment section. If you're a student who is struggling or trying to improve in all your STEM related courses, whether you're in middle school, high school, or college level, just make sure you email me at shuhabi@gmail.com. I help students succeed and be the best version of themselves, as well as assist them navigate their academic life. So if you would need my services, email me at shuhabi@gmail.com. Also, make sure you click into the description box. I have done a bunch of these physical chemistry questions from the Physical Chemistry Atkins 11th edition. So the playlist in the description is going to be of use to you, as well as if you'd want to purchase this book, click on the link below. The book we're using again is Physical Chemistry 11th edition, the Atkins Physical Chemistry 11th edition. Don't forget to like and subscribe. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.